Hi, and welcome back to this series of videos about how computers work. If you're interested in building your own retro console by supporting the Retcon project, remember to like and subscribe and to sign up to get updates about the crowdfunding campaign. So this video is all about how computers represent numbers, and in particular it's about two types of number that you might have heard about, binary and hexadecimal numbers. Now in these videos I try and make everything as accessible as possible, but I do have to tell you that this video is a little bit more numerical than most of them. I do appreciate that numbers aren't really everyone's cup of tea, so if you want to sit this one out, it's not the end of the world, you should still be able to follow along with the other videos just fine. So binary numbers are essentially the numbers that computers use to count and do maths. And the first question I'm going to try and answer is, why binary? Why don't computers just count like you and I do? The way that most of us count is using a system called the decimal system. It's called decimal because it's based on the number 10, and we think the most likely reason for that is that, well, most of us have 10 fingers on the end of our arms, but computers don't have fingers or arms. What they do have is electrical connections in the form of wires, copper tracks on PCBs, and inside the microchips that they're made of, connections made of silicon. All the information that computers process needs to flow along those connections in the form of electrical signals, and we need some kind of system to decide how to translate those signals into something meaningful. In analog electronics, we vary voltage or current continuously to transmit information, but in digital electronics, we only use a fixed set of values, just like when we count on our fingers. In fact, the word digital comes from the Latin word for finger. The number of values that we use in digital electronic systems can vary. By far and away, the most common number of values used is 2, because it's so easy to make and use systems which use only 2 values. These are called binary systems, the word binary coming from the number 2. We usually refer to the 2 different binary values as being either on or off, high or low, or 1 or 0. You might think of this stuff as a very recent invention, but arguably one of the most famous digital communication systems was in use as early as 1844. The telegraph, using Morse code, can be thought of as kind of the internet of its time, and it revolutionized the way that people communicate with each other. The idea was that you had a very long piece of 2-core cable with a switch at one end and an audible or visual device at the other end, and by sending a series of ons and offs with different timings, telegraph operators were able to encode and decode messages using any of the alphabetic characters in the Morse code. Telegraphy is an example of what we call serial communication, meaning that we send information down the communication channel one piece at a time. Now, that's really all we can do when we have just one wire to work with, but it does mean that we have to wait until we've got all the bits of information before we have the whole message. Luckily, computers have space for more than one wire inside them, so we can send multiple bits of information at the same time. This is what we call parallel communication. If you watched the last video on CPUs and RAM, you might remember that information between the CPU and memory travels along a set of wires called a bus. And we also saw that the Z80 CPU has a data bus that's 8 bits wide. That means that the 8 bits of information traveling along the Z80's data bus form a parallel communication channel. Where binary numbers come into all this is when we want to have the 1s and 0s traveling down those parallel wires represent a number in the real world. In this sense, binary is a form of encoding, just like Morse code, except that Morse code encodes for alphanumeric characters, that's numbers and letters, whereas binary encoding only encodes for numbers. One approach we could take in coming up with a binary encoding scheme is to assign each number an arbitrary combination of 1s and 0s, a little bit like Morse code appears to do. In fact, Morse code isn't totally arbitrary. It assigns shorter codes to those letters which are used most commonly in the English language, and longer codes to those letters which are used less frequently. But there is a problem with using an arbitrary code. We actually want our encoding to have other useful properties, like allowing us to really easily do maths on the numbers in their encoded form. The answer to this problem is actually really profound, and to understand it properly, we're going to have to take a deep dive into how we all count. As we said earlier, the way that most of us count is using a number system called the decimal system. Other names for it being base 10 or radix 10. And the reason for the number 10 is that there are exactly 10 symbols that are used to make up all of the numbers that we use. These 10 symbols are the 9 numbers from 1 to 9 and the special number 0. Try and think of any positive whole number that uses any symbol that isn't one of those 10. If you can, please write it in the comments below. I'd be interested to hear about it. Now human beings have had the symbols 1 to 9 for a very long time, but trying to count with just those 9 symbols is kind of tricky. It's the innovation that led to us using the number 0 and something called the positional notation system that really changed the way we count. And we think that happened in around the 4th century, leading to the 10 symbols that we use today. The way it works is something everyone's probably familiar with, even if they've never thought about it in much detail before. We start off with the number 0, which is the first counting or natural number. And then we run through the other 9 numbers in order. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It's when we get to the number 9 that the fun really starts. And the problem is that we've run out of symbols. If we want to unambiguously write down a number that's 1 more than 9, we're going to have to invent something new. Rather than invent a new symbol, the positional notation system does something quite inspired. It says, well, let's go around in a circle from 9 back to 0 again. But to keep track of the fact that we've done this, we're going to create a new column to the left of the first one. This new digit here, which is now 1, counts the number of times that we've had to pass 9 and go back to 0 again in the first column. So far we've passed 9 once, but if we keep on counting, we'll see that happens again and again every time we reach 9 and circle back to 0. In a very real sense, this new column is counting the number of times we've counted to 10 in the column before it. That's why in primary school maths we call it the tens column. We call the first column that we started with the ones or the units column. If we carry on counting, we'll eventually reach 99, and we'll see that we've run out of symbols again, this time in both the units and the tens column. So we pull the same trick that we did last time. We reset both the units and the tens back to 0, and to commemorate the occasion, we'll start a third column that we'll call the hundreds column. Each new column that we invent tells us how many times we counted to 10 in the column before it, so we have thousands, tens of thousands, hundreds of thousands, millions, and so on. This focus on the number 10 is why the decimal system is so called. There are exactly 10 symbols, and each column counts groups of 10, the so-called powers of 10. But there's nothing inherently special about the number 10. If human beings had evolved with, let's say, 7 instead of 10 fingers, we could have easily invented another counting system which worked in the same way, but with 7 instead of 10 symbols. But what if instead of 10 or even 7 symbols, we only allowed ourselves 2? In that case, we can still apply the same rules of positional notation counting, and we'd have invented binary numbers. Let's try it out. We start, just as in decimal, with a 0, and from there we count up to 1. So far so good. But wait, we've already run out of our 2 symbols, so we'll pull exactly the same trick as we did in decimal. We roll the first column round to 0 again, and make a new column to the left to track how many times we've done it. At this point, we've only counted 2 numbers up from 0. So the binary number 10 is the second positive number in binary, and so it's equivalent to the decimal number 2. Just take note here, when I read out the number 10 in binary, I don't say it as 10. That's to avoid confusion between decimal and binary. Okay, so we only got to 2. What comes next? Well, we do have room to increase the units column by 1 here, so the third binary number we can write as 11. That's equivalent to decimal 3. At this point, we've run out of numbers again in both our columns, and we need to create a third one. We do exactly the same thing as we did in decimal when we reached 99. We reset both columns to 0 and put a 1 in the new column, giving us the fourth binary number 100. This process continues just as it did in decimal, except instead of each column increasing when the one before it goes past 9, it does it when the one before it goes past 1. Here are the first 16 binary numbers, and the first 256. When we write down all the numbers like this, we can see some really interesting patterns emerging. Firstly, each column seems to flip between 1 and 0 at half the rate of the one before it. The units column flips on every count, but the second column only flips every other time, and the third column every fourth time. Actually, we see the same thing happening in decimal, except that in decimal, each of the columns increases at a rate of 1/10 the one before it. Another thing that we might notice is that we can take any binary number and put a 0 at the end of it, and what we'll end up with is a number that's twice as much as the number we started with. For example, let's take a look at 111, which is 7 in decimal. If we put a 0 on the end of it, we end up with 1110, which is 14 in decimal, and 14 is twice 7. Similarly, 101 is 5 in decimal, and if we put a 0 on the end of that, we end up with 1010, which is 10 in decimal. Again, we do see the same kind of effect in decimal, except that in decimal, when we put a 0 on the end of something, it multiplies it by 10 instead of 2. There also seems to be something special about numbers which start with a 1 and all the rest of the digits are 0. As we just saw, adding a 0 on the end of a number multiplies it by 2. So these numbers go 1, 2, 4, 8, 16, 32, 64, and so on. These numbers are the powers of 2, and they're analogous to the powers of 10 that we see in decimal. In fact, we can express any binary number as a sum of its powers of 2, just like we can express any decimal number as a sum of its powers of 10. If we look one down from the powers of 2, we can see numbers that are made up entirely of 1s, and these represent the largest binary number that we can count to with a given number of digits. For example, let's say we have 8 wires, like in the Z80's data bus, then the largest binary number we can represent with those 8 wires is 8 ones, or 255. Again, we can see the same kind of thing happening in decimal. If we have a number that's made up of 4 digits, the largest number that we can count to with that is 9,999. And that's really all there is to binary. I think it's incredible and even beautiful how everything about the way we count seems to stay the same with positional notation number systems, even if we completely change the number of symbols that we're working with. The only thing that is different between decimal and binary, for instance, is that everything special that seems to happen around the number 10 in decimal happens instead around the number 2 in binary. Now you might be wondering, what about negative numbers? Well, that's a little bit trickier to get our heads around, so we're going to revisit that in another video when we look at addition in binary. Now one thing you may have noticed about binary is that it takes way more digits to write down a number in binary than it does in decimal. Even with numbers as low as my age, that's 21, we need twice as many digits to write it down. When we get to 255, we need 8 binary digits compared with just 3 in decimal. And to write down the longest address in the Z80's 16-bit address space, we need over 3 times as many digits in binary than we do in decimal. What's more, long strings of 1s and 0s are quite hard for us to read, let alone remember. The problem here is that having fewer symbols means that there's less information per symbol, and so we need more symbols overall to carry the same amount of information. If only there were a number system that computers could easily understand that wasn't so unwieldy for us humans. Well, there are some, and the most common one is called hexadecimal, or base 16. We arrive at base 16 by starting off with binary. Let's look again at a 16-bit binary number. The reason binary works so well in computers is that each bit in a binary number can correspond to precisely one wire in a computer. But what if we decided to take groups of wires instead of individual wires? Let's say we group them into 4s. We'll notice that there are exactly 16 combinations of 4 binary bits, and so we can assign each combination a unique symbol. The first 10 symbols we can simply use from the decimal system, like this. But what about the last 6? Well, we do have a whole alphabet to work with. Why don't we just borrow the first 6 letters from the alphabet? We'll say that the symbol A corresponds to binary 1010, B corresponds to 1011, and so on, with the symbol F corresponding to 1111, the last of our 4-bit groupings. With these mappings, we can now write our 16-bit binary number as a much shorter 4-symbol version. Because we have exactly 16 symbols here, we've actually invented a new number base. It's base 16, or hexadecimal. And as we've seen already, the rules for counting are exactly the same in positional notation systems, regardless of the number of the base. Let's see some hexadecimal counting in action. It's important to understand here that computers don't really work in hex. They effectively work in binary, but because hexadecimal is based around 16, which is a power of 2, it's really easy for us to convert between hexadecimal and binary by just grouping 4 binary digits together and remembering our symbol mappings. Once in hex, the numbers are so much easier for us to write down, remember, and talk about. As an illustrative example, instead of telling you that I put the number 10000000 into address 1100101110001111, I can just say that I put the number 80 into address CB8F. Much easier. Now you may be thinking, couldn't we have chosen a different number of bits to group by instead of 4, let's say 3 or 5? Well, yes we could, and in fact grouping by 3 gives us base 8, or a number system called octal, which was more popular in the early days of computing. And there are some human cultures in the world which do use octal every day for counting instead of decimal. It just so happens that grouping by 4 gives us quite a nice compromise between the number of symbols that we need to memorize, that's 16, and the total length of numbers that are represented in that base. To end this video, I thought I'd take a few minutes to talk about a really common use of hex that many people will be familiar with, digital color codes. Our perception of color is just our eyes responding to different wavelengths of light. And it just so happens that different cells in our eyes are particularly sensitive to the colours that we perceive as red, green and blue. Mixing these wavelengths then gives us the easiest way of creating a wide range of colours that we can perceive, and it's why optical displays like TVs or LCDs have 3 colour elements per visual screen element. When we want to display a colour on a screen, we do so by specifying the exact amount of red, green and blue that we want to mix together. We call each of the 3 colours a channel, and the range of values that we can assign to each channel we call the colour depth of that channel. For example, if we use 8-bit binary numbers to represent each colour channel, then we say that we have a colour depth of 8 bits per channel, or 24 bits overall. 24-bit colour, sometimes called true colour, has for many years been the gold standard of digital colour display because it allows for over 16 million colours, which is more than the 10 million colours that the human optical system can differentiate. As an example, here's how we would encode the shade of orange used on the Retcon website in 24-bit colour. The value of the red channel is 191 out of a possible 255. The green channel is 55 out of 255, and the blue channel is only 10 out of 255. Now if we write that down in binary and group the digits into 4s, we end up with the hex values. That's BF, 3A, and 08 respectively. Sticking those 3 hex values together and putting the hash or pound sign in front to tell the computer that it's a hex value, we end up with the familiar hex color code that we see in digital design. Just double checking on a popular website, and sure enough, we see that the hex code BF3A08 does indeed describe the Retcon orange. Well, that's all I have for you today. If you've got any questions or comments about binary or hex, please do drop me a line below, and do remember to like and subscribe if you haven't already. See you later.